Hello, welcome to the Computational Storage Security Call to Arms and Opportunities for the SNIA Storage Security Summit. I'm Bill Martin. I am the editor of the SNIA Computational Storage Architecture Specification and the Computational Storage API Specification, as well as the co-chair of the SNIA Technical Council, and I represent Samsung Semiconductors. With me today is Jason Molgaard, who is the co-chair of the SNIA Computational Storage Technical Work Group. I'd like to start out with the standard legal notice. I will not read the entire legal notice to you. The most important piece of this is that there are no warranties, express or implied. Use this material at your own risk. Jason and I will try to be as accurate as possible, but we are not legally responsible for anything we say. And with that, I'd like to turn it over to Jason, who will be describing to you what is computational storage.
Yeah, thank you, Bill, for that introduction. So definitely we want to start our presentation by giving an overview of computational storage, just so that we're all on the same playing field and speaking the same language. So if we think about traditional storage devices, the architecture has been largely unchanged for quite a number of years, for a very long time. You'd have a central CPU that would bring in data from a storage device and process on it, and then write that data back out to storage. If we go to the next slide, with computational storage, what we would like to do is offload the host or reduce data movement from that traditional storage model. So taking a look at this diagram on the right-hand side, there's kind of two sub-diagrams. Starting with the left-hand side of this diagram, you'll notice that there is a compute level that's inserted between the host CPU and the traditional storage device. And the objective, of course, is to offload that host CPU and reduce that data movement exactly as we have described. Looking at the diagram over on the right-hand side, that compute is a little bit lower down in the drive itself. You'll see it's embedded into the storage device, but it's still functioning as a similar purpose to offload that host CPU and reduce the amount of data that's being moved. So if we go to the next slide, we'll start with some definitions that kind of help set the stage for all of the things we're going to talk about. So there's 4 definitions on this slide, starting with the computational storage device, also known as a CSX, where X is, the unknown. So it can be any one of the next 3, the computational storage processor, which is a CSP, a computational storage drive, or a CSD, or a computational storage array, or CSA. So a computational storage processor contains a computational storage engine, but does not have any persistent data storage. So a computational storage engine is a term that we'll get to in an upcoming slide, but I'll just give you a little bit of an overview. It's essentially the logic that can perform computations, be programmed to perform those computations. You could think of a general purpose CPU as an example of a computational storage engine, or perhaps an FPGA as another example of a computational storage engine. Either way, they can be programmed to perform computations. So the computational storage processor has one such engine, or at least one such engine, but doesn't have any storage. The computational storage drive, on the other hand, has that same computational storage engine and the persistent storage. So thinking of the slide, the previous slide, the diagram over on the left would be a computational storage processor. The diagram on the right would be a computational storage drive. And then finally on this slide, the computational storage array, similar to the name may suggest, it is a traditional storage array that also has one of these computational storage engines in it for performing compute on the drive itself without moving it to the host CPU. So moving into the next slide, we've broken these down diagrammatically, these 3 different descriptions. So on the left, we've got the computational storage processor. In the middle is the computational storage drive, and on the right-hand side is the computational storage array. And you'll notice that all three of these pictures have a teal colored box and sub-blocks labeled computational storage resources. I'll get into that in a little bit more detail on the next slide. But for now, if we focus on what's similar or different between these three diagrams, you'll notice that the computational storage processor it does not have that persistent storage like we had mentioned. Whereas if you look at the computational storage drive, it has a storage controller and it has the device storage. One key point about the computational storage processor that is useful to keep in mind as our presentation progresses is that the only way that the computational storage processor is able to access the data is through peer-to-peer communication with a traditional storage device that's going to be connected up over the fabric. And so it's going to be making those requests for communicating directly with the drive peer-to-peer, whereas the computational storage drive is able to make those requests internal to itself. The computational storage array, as I had mentioned, it is a traditional storage array with these computational storage resources. We probably won't spend a lot of time focusing on that in our presentation, but just for completeness, wanted to make everyone aware of that technology. So now if we go to the next slide, we can kind of delve more deeply into that teal colored box that's labeled computational storage resources. So the computational storage resources are the resources that are both available and necessary to be able to execute a computational storage function, also known as a CSF. A computational storage function is the specific operation that you want to perform on the data that can be executed by a CSE or a computational storage engine. So you can think of this is the program that you want to run. The computational storage function is the program. So, and I'd already mentioned earlier, the computational storage engine, you can think of as a general purpose CPU or something that can be programmed to execute those functions. So a new block that we haven't talked about yet, but is shown over here on this left-hand side is the Computational Storage Engine Environment, or CSEE. So this is an operating environment space for the computational storage engine. So again, if we kind of think of our analogy where the computational storage engine is a general purpose CPU, the computational storage engine environment would be the operating system running on that CPU. And the computational storage function would be the application that runs on the operating system that's executing on that. So whatever that function is, it likely needs some memory. And so we have again, in this teal colored blocks, we've got FDM, or function data memory. So this is memory that's available for that function to use as scratchpad or data storage, temporary storage, whatever is necessary as it's executing. And in particular, some of that function data memory, when it's allocated to a specific function, it is now termed allocated function data memory because it has been specifically allocated to that computational storage function. Now, the last block on this teal colored box that I haven't touched on is the resource repository. The resource repository is the block that contains resources that have not been activated yet. They've perhaps been downloaded to the drive, or they already exist on the device, but they're not currently available. They haven't been activated, but they are there and could be activated. So if we go to the next slide, we'll kind of walk through a little bit very briefly the flow that would happen with a computational storage drive as it relates to all these terms that we've just described. So this particular example is a case where we've got two computational storage engine environments that is in the host, and they need to be downloaded from the host into the drive to be made available. So everything powers up, the host comes to life, and it downloads CSEE1 and CSEE2 from itself into the resource repository. And so if we look at the diagram over on the right-hand side, you'll see arcs labeled A and B, and those are the two CSEEs that are being loaded into the computational storage resource repository. And you'll also notice that computational storage engine environment 2 happens to have computational storage function 1 contained within it. And we'll get to that a little bit more in a moment. So now that we have those two CSEEs that have been downloaded into the resource repository, we wish to activate them. And we do so, we activate them and say they are going to execute on computational storage engine CSE that happens to be shown here. This example only has one. There certainly could be more, but for simplicity, we're showing the one. And both these CSEEs are now activated on that CSE if we follow arcs C and D in this diagram. So because CSEE2 has CSF1 built into it, CSF1 begins executing. And it needs some memory, some function data memory. So it's allocated some function data memory as shown over on the left side of this diagram. There's kind of a blue dashed arrow that points over to that. And what's happening with this function is it's bringing in data from the persistent storage, from the device storage, which is the blue dashed ARC1, processing on it, and then writing that data back out to the storage following blue dashed line or ARC3. So the data is moved in and out of the storage, in and out of that AFDM. The CSF1 operates on it and produces the results that that particular CSF is programmed to generate. So as security experts, you're probably looking at this and you may have some concerns already coming to mind in your head. Well, and so that's where I'm going to turn it back over to Bill now, who's going to talk about some of the security concerns that we've identified in the computational storage twig and where we should go with them. Bill.
Thank you, Jason, for the introduction. It will be very helpful as we go through and talk about the possible areas of security concerns that exist. So this is broken into 3 sections. The first of these is near term. What are we concerned about today in implementations that we expect to be shipping in the near future? And how does that affect our overall architecture? So in the near term, what we're looking at is fully constrained systems. So we're looking at systems that we believe have less in the way of security concerns because of how they are implemented. So this environment consists of a single physical host. Within that physical host, we only have one virtual host, and that has one or more CSXs connected to it. The host is responsible for the security of the ecosystem. What that means is that we are relying on the host to have administrative controls that only allows administrative functions to be done by a valid administrator or a valid administrative program. Next, we are talking only about physically secure attachment between the host and the CSX. What this means is we don't have to worry about a man-in-the-middle attack. How do we prevent or provide security for a man-in-the-middle, for someone who has gained access to the physical connectivity of the CSX to the host? We're talking about CSX security requirements that are comparable to the security requirements common to SSDs and HDDs and are managed under current SSD security paradigms, for example, the TCG Opal drive spec. So we are attempting to rely on existing security that is in the system to manage secure connection to a drive to be the security that we can rely on for this first near-term computational storage system. It is important to note this system relies on the host and existing SSD security paradigms to provide the security. We are not defining specific security protocols for this near-term landscape. As we go into the intermediate term, we're looking at something that is a little bit more complex, but not the whole kitchen sink of complexity. This environment, again, consists of a single physical host, but that host now has 2 or more virtual hosts. This provides some more security concern points, some more places where we should be thinking about the security of the system. We are still talking about a physically secure attachment between the host and the CSX. So we are in the intermediate term, not thinking about how do we provide security over an unprotected connection between the host and the CSX. So what are the areas of concerns? You'll see some bullseyes here that talk about different areas. This first possible area of security concern has to do with downloaded programs, and actually a little bit more than that. It has to do with all of the downloads that are coming from the host. As Jason talked about earlier, you have the ability here of downloading a computational storage environment. You can have a computational storage environment that contains a computational storage function, and you can also have just a download of a computational storage function itself. So what do you have in terms of security concerns? The first and probably most obvious is you have a virtual machine running in the host. If it has a rogue program or function that it downloads into this resource repository and then activates on a computational storage engine, you have the ability to do whatever operations that rogue function or program allows you to do, meaning that you can break into security in a variety of ways. The next issue is, what about a broken program? While this may not be used as an attack, it still provides a security hole that the broken program could do things to break or open up security issues within your environment. You also have the possibility of a corrupted download. What happens there? You need the security of making certain that you have not allowed a corrupted download to provide possibly a security engine environment or computational storage engine environment that has the ability to do something destructive or harmful to the system. So there is verification required for downloaded code. Then the next thing is, as Jason talked about, the computational storage engine could be a CPU. That CPU could be running an operating system. Operating systems often have vulnerabilities within them. That's why you get new downloads for your operating system periodically. The same thing now applies on your computational storage device of the fact that you are potentially running an operating system. So you need to make certain that that operating system is updated with your latest security updates. So our next area that we talk about is, what about the shared memory? So you have this device memory. It is being shared by multiple functions that are running and multiple instances of a function that are running that are accessing data in that memory. So Jason talked about the fact that you can have allocated function data memory, and that allocation allocates some amount of physical memory to be used by a particular instance of a computational storage function. So what happens when you get leakage from one computational storage function to another? How can that happen? There are multiple ways that that can happen. One of them is if your allocation allocates the same physical memory to two different allocated function data memory blocks for two different computational storage functions. To me, that would be a design error in your design. But some other things to consider is what happens to that physical memory when you deallocate it. And now you come along and you allocate function data memory again, and it happens to be allocated to that same physical memory. You now have the potential of access to that memory after the CSF is no longer active and no longer utilizing it. The next area is what about corruption of memory by the CSF? So again, if you have a rogue CSF or a broken CSF or any sort of issue with your CSF, you have the ability to corrupt the memory. Now, the biggest thing here is our anticipation, or the architectural goal here is that the CSF is only allowed to access the allocated function data memory that it is allocated. But you have to have insurance that the CSF cannot access any memory outside of that allocated function data memory. Another possibility is denial of service by a CSF consuming all memory. And this is actually partly on the CSF point and also partly from the standpoint of a virtual machine that is responsible for allocating function data memory. The virtual machine should be the one which is allocating the function data memory, but if it chooses to allocate all function data memory to a single CSF, that leaves no more function data memory for any other CSFs to utilize. So that can in turn mean that all other CSFs are blocked from actually executing. So that's another path from the virtual machine to the device that can cause denial of service. Next, I'd actually like to skip to the last bullet, which is key storage and memory. You have the potential of needing to use keys for various purposes. We'll get into a little bit more of that on future slides. But if your keys are stored in the device memory, there are a couple of things that you need to be careful of. One is that you don't allocate the function data memory in such a way that someone who is not supposed to have access to a given key does have access. And how are those keys managed? How are they put into device memory? How are they allocated or associated with a specific computational storage function? So all of those issues. And finally, we need, as we move forward to this more complex system, we need to consider the fact that you may need to sanitize your device memory in order to repurpose this computational storage device for some other future purpose. So the next is, what about the device storage? What happens in particular if on your device storage you have a self-encrypting device and the data is encrypted? You need to provide a mechanism for secure key distributions to your computational storage functions so that the computational storage functions can access the particular device storage that they are allowed to access. And you have to ensure that the process of moving data between your allocated function data memory and device storage is secure, is only done to the area of that device storage that you are allowed to access. So there are security issues around that that need to be considered. Next is, what happens if you have a rogue CSF that intercepts the keys that you're using and can utilize those to decode device storage, or possibly encode all of the data on your device storage, opening a hole for ransomware attacks. So need to consider how keys are dealt with in terms of the keys for the device stored that is encrypted or even unencrypted data then being encrypted by a rogue CSF. One of the paths that this particular diagram doesn't show is the architecture would allow a CSF to directly operate on data that is stored on device storage and to store the data back onto the device storage. While that is not our expected use case, that is a potential within the overall architecture. So the final thing is the potential for a CSF to corrupt data on the media. And this may be intentional corruption, or this may be accidental corruption due to programming errors, etc. But there is an issue that we need to look at. What are the security implications to prevent a CSF from corrupting data on the media? The last one, and this gets into the different configuration that Jason mentioned, where you have a computational storage processor. That processor does not have any storage locally. It is accessing that data across a fabric. This could be a PCI fabric. It could be PCIe over fabric, or sorry, NVMe over fabric, or any possible combinations of fabrics. And the question is now, how do you secure that transaction? If your SSD in this particular configuration is an Opal drive, then your computational storage processor would actually be acting as the host that is connected to that Opal drive. Now, an Opal drive, in my understanding, is only allowed to connect to a single host. And this CSP would be the single host that is connecting to that Opal drive. Now, what do you have to do in order to do this? You now have to have management of credentials, and that has to be done on the CSP. You have to be concerned about the security of the credentials on the CSP. But an opening that this brings in is if the communication between the CSP and the SSD is shared between multiple hosts, between the CSP and the host is shared between multiple hosts, you now have to deal with the fact that you are in essence allowing multiple hosts to communicate with a single SSD that is an Opal SSD that has an assumption that only one host is connecting to it. Now, that could indeed be a valid configuration, a valid operation where it is truly secured to the CSP, but the CSP now has to secure its communication with the host and authentication and authorization for access to any given SSD that it may be connected to. Finally, you do have to make certain that the communication between the CSP and SSD are secured, in particular if you're going over something other than just a local fabric. However, for the intermediate term, we are still considering only configurations that have a single or a secured connection between the host, the CSP, and the SSD. So all of those are the intermediate term. We have not started addressing those yet. As we get to the summary, Jason will talk about how you can help us look at the intermediate term. Long term. The long term I've broken this down into 3 slides. I'll try to cover them relatively quickly because this is the long term, but you can see you can get into a very complex configuration. And in this configuration, there are certain things that are management related activities, such as the download of CSEE, the allocation of function data memory, download of CSFs, activation of CSFs. All of those things are management type issues. Now, there are a couple of ways that we can look at securing that. First, you can have a fabric management device that has secure, authenticated capabilities with the computational storage device, which is shown here as a processor. However, the processor has direct connection to storage. So in this configuration, you can have the host send its requests to the fabric manager through some sort of authenticated mechanism, and the fabric manager being authenticated with the computational storage device is the only entity that can do these management functions. The next possibility is that the host itself is authenticated with the computational storage device and authorized to perform the computational storage management applications of downloading, allocating, etc. This requires discussion and figuring out exactly how that authentication is done and all of the mechanisms related to that. The final issue is, as you get into this larger configuration, you now have the possibility that your storage is across a fabric. The fabric may not be secure, and the issues of security of how you talk across that insecure fabric to your storage and provide security for the data on that storage. And that's yet another large area of discussion. As I've said, these 3 figures are somewhere out in the future, but they are things that we do need to be aware of and thinking about how we deal with them. So with that, I'd like to turn it back over to Jason to give you kind of an overview and a call to arms for us.
Yeah, thank you, Bill. So if we go ahead and move to our summary slide, I think that there's kind of a couple of important call to arms that we need to take into consideration. So first of all, for the storage producers out there, there's a big call to arms as you're making computational storage devices or coming up with your own implementations, that you can't ignore security. Security is paramount, and it's going to be critical that it's done correctly, or it may be an unsuccessful product, or worse yet, it may damage computational storage as a technology, and we certainly don't want that. From the security community, as Bill had mentioned in the presentation, I think there's a lot of opportunity for the security community to kind of jump in and help us out. We've clearly opened up some new attack surfaces by creating computational storage and moving that compute down into the drive, making it available potentially over NVMe over fabrics, thinking long-term from some of the material that we just covered in Bill's discussion a moment ago. So our request for the security community is to come join us, come join the SNIA Computational Storage Technical Work Group and help us to kind of identify all these security issues or concerns and find solutions for them. We're not looking to invent new security protocols or standards by any means. We want to leverage everything that's out there. I think the key is to identify the issues and then find the right protocol or technology or standard that can be applied to mitigate that concern and have a successful and safe, secure computational storage development. So again, if you're interested, please do come join us. But overall, Bill and I are very optimistic about computational storage and that it can be done with appropriate security. We think that there are opportunities, they do exist to manage computational storage device security. We've got some ideas that we're already working as a technical work group. Certainly your input may help ferret out anything that we've overlooked. But we have a lot of optimism that we can get there from here. And with your help coming, then we would potentially have even more success. And then finally, we think that a computational storage device with security done well may present opportunities to help facilitate device security of a broader system. So thinking in terms of those long-term diagrams, that if the computational storage security is correct and you've got some sort of edge deployment with your computational storage drive connected up over Ethernet, that that security may help bolster the security of the overall system and become part of the solution for that security moving forward. So we're very enthusiastic about that and think that that may be a solution feeding back into the storage community overall with computational storage done well. So with that, that concludes our presentation. We would request that you please take a moment to rate the session and let us know what you think. On behalf of Bill Martin, I'm Jason Molgard. Thank you for joining us for this presentation, and we hope you have a wonderful rest of your day.